Now, horizontally simple regions are going to have iterated integrals that look more like this. The integral from c to d, integral h1 of y to h2 of y of some function of x and y, dx, dy. Now here again, we can use context clues, knowing that the outer differential corresponds to the outer integral. These bounds from c to d are corresponding to y, so y equals c to y equals d. And on the inside, it's x, which is going from h1 of y to h2 of y. In terms of pictures, things are going to look like this. Along the y-axis, we're staying between c and d. And then to the right of that, I'm going to have the graphs of two functions, x equals h1 of y, and x equals h2 of y. So keeping myself between c and d. This would be the horizontally simple region that I was describing using these bounds. So let's look at an example of carrying out an iterated integral in this order. Let's say that we want to integrate 0 to 1, integral y squared to y, x plus y plus 1, d something, d something. Notice that this inside bound has got to be an x. This is clearly here, x is equal to y squared, and x is equal to y. And the outside bounds have to be y. So in this order, y is on the outside. The inside bound can depend on the variable that's further out. So the x bounds may contain y's in them, but the y bounds have got to be numbers, because I want to have a number as my answer. So first of all, we're going to carry out the integral on the inside. Integrating with respect to x, treating all the y's as constants. So we're integrating from 0 to 1. Integrating with respect to x, I have 1/2 x squared plus, since I'm treating the y as a constant, y times x, or xy, plus the integral of 1 with respect to x is x. And I take that from x equals y squared to x equals y. I'll plug in the endpoints and subtract, and then whatever I get, I'm going to integrate with respect to y. So first of all, let's go through and replace all the x's with y's. That'll give me 1/2 y squared plus another y squared plus y minus, and I'm going to replace all the x's with y squareds. So it's 1/2 of y squared squared, which is 1/2 y to the 4th, plus x times y squared, which will be plus y cubed, and replacing this x with y squared, y squared. Let's see if we can combine some like terms before we integrate again. Actually, one thing I see is that I have a y squared minus a y squared. So those two cancel out. And then I have a y to the 4th, a y cubed, a y squared, and a y. None of those are like terms. So 1/2 y squared plus y minus 1/2 y to the 4th, and I'll distribute the minus sign to get minus y cubed. I'll use the power rule to integrate each one of these. The integral of a half y squared, oops, I'm integrating now, is going to be 1/6 y cubed plus the integral of y is a half y squared minus the integral of y to the fourth is 1/5 y to the fifth, so this would be 1/10 y to the fifth minus a fourth y to the fourth. And this is going to be taken from y equals 0 to y equals 1. Plugging in 1, I get a sixth plus a half minus a tenth minus a fourth. And of course, when I plug in 0, I get 0. So let's see, what's the common denominator here? Looks like it's going to be 60. So 10 sixtieths plus 30 sixtieths minus 6 sixtieths minus 15 over 60, which is 40 minus 21, 19 over 60.